Swayam Prabha. Digital India. Educated India.
Welcome back to our lecture series on advanced hydraulics, part of the NPTEL program, phase 2 program. We are in the third module on varied flows. We have finished 10 lectures in this module. Today is the 11th lecture, and by today's lecture we hope to wind up this module. In the last class, we had discussed on the concepts of spatially varied flow. We had derived the dynamic equation for spatially varied flow for increasing discharge. That is, first using the continuity equation, we identified what is the rate, that is the rate of increase in discharge per unit length, that was identified. It was given by the following expression. Then subsequently, using the momentum equation, we had derived the dynamic equation for spatially varied flow. I hope you recall all the terms here. Y is the depth of flow, S0 is the bed slope, SF is the friction slope, capital Q is the discharge, Q star is the rate of increase in discharge per unit length, G acceleration due to gravity, area A is the area of cross section, again T is the top width of the channel. All these things are self explanatory. Similarly, we had discussed on the dynamic equation for spatially varied flow for decreasing discharge. If there is a continuous decrease in the discharge through a channel, then using the energy principles, we had derived the corresponding equation, dynamic equation. Also, we have suggested how to use numerical methods, that is, numerical methods can be applied to solve these two types of dynamic equations. From solving these dynamic equations, either we can get the depth of flow at various cross sections, or you can get, say, for a specific depth at which cross section it is available, that depth of flow is maintained, and all that can be readily obtained. Today, we will be dealing with the concepts on, or some of the features on spatially varied flow and its profiles. So, as discussed earlier, the dynamic equation for spatially varied flow in the case of increasing discharge, we had derived it using momentum principles. It was given in the following form. So, if you look closely into these things, this has been given without the momentum corrections applied to the cross section. So, if any cross section is there, then we have taken the average velocity across this cross section as a parameter, and based on that average velocity, whatever correction for the momentum is there, that was not incorporated. We had taken momentum correction factor beta is equal to 1, and we had developed this equation. So, usually the momentum corrections are very much significant in spatially varied flow. Therefore, we have to apply the momentum correction factor, and the improved or modified dynamic equation will look like this. That is, dy by dx is equal to S0 minus SF minus twice beta q q star by G A square, the whole thing divided by 1 minus beta q square t by G A q. So, beta, the momentum correction factor, is incorporated in the dynamic equation. Subsequently, a similar concept, similar principle can be applied for the dynamic equation for decreasing discharge. We had derived it using energy principles earlier in the following form. So, as we have mentioned here also in the cross section, the corrections for energy are not incorporated. So, we need the energy corrections for specially varied flow, because there is a rapid change or rapid decrease in energy due to the change in flow and all. So, rapid decrease in the sense that some changes in the energy is occurring due to the change in quantity of water and all. So, you need energy corrections also. Therefore, with energy correction factor, the dynamic equation can be specified as given here, dy by dx is equal to S 0 minus S f minus alpha q q star by g a square, the whole thing divided by 1 minus alpha q square t by g a q, where your alpha is the energy correction factor. I hope you recall these factors, we had studied them in detail in module 1 and all. So, if you look into both the equations, say dy by the momentum means dynamic equation derived through the momentum principles, as well as the dynamic equation derived through the energy principles, both of them can be written in a common form. So, I have just expressed this thing in a common form here, dy by dx is equal to S 0 minus S f minus a quantity C 1 into q q star by g a squared by the whole thing divided by 1 minus C 2 q square t by g a q, where C 1 is equal to twice beta and C 2 is equal to beta when we use dynamic equation for increasing discharge. Similarly, C 1 and C 2 both are equal to alpha when we use dynamic equation for decreasing discharge. So, it is up to you, just for the convenience we have written it in a common form. So, for analyzing the flow profiles in a spatially varied flow, let us first consider through a simple example. So, let me state the example. There is an horizontal rectangular channel that collects water laterally through the overflow spillway. That is, water is entering the rectangular channel through overflow spillway like this. It is entering like this, say maybe from both sides. This rectangular channel has a free fall overfall outlet like this. It is the at the end of this rectangular channel, the water is falling freely. Inflow is uniformly distributed along the channel length. So, the inflow to this channel, it is distributed uniformly at a rate of q star per unit length. Now, derive the equation of flow profile. You can ignore the friction losses. How will you try to obtain the flow profile or the equation for the flow profile? So, this is a very interesting problem. You can see that this is a horizontal channel, means water is coming into this channel. The length of the channel, let us assume it as capital L. Then the width of the rectangular channel is capital B according to our normal convention. Depth of flow at any location, it is y, right. So, based on this, how will you obtain the flow profile? So, again the cross section, we have our rectangular channel, B is the width, y is the depth of flow. So, B and T both are same for the rectangular channel. Now, read the question carefully. What are the assumptions or what are the things given here? There is an assumption that you can ignore friction losses. So, what does that mean? While ignoring friction, to ignore friction losses means you are considering SF is equal to 0. Another criteria given is this is a horizontal rectangular channel. So, that means your bed slope is also equal to 0. Therefore, your dynamic equation now this becomes dy by dx is equal to both S 0 and S of r 0. So, minus 2y's, okay. I am just taking the common form. Okay. Is it sufficient? Common form of the thing. So, minus, or let me say as this is a case of increasing discharge. So, let us see. So, this becomes minus 2 q q star by G A square, the whole quantity divided by 1 minus q square T by G A Q. We are assuming that the momentum correction factor, it is approximately 1 for only for this particular problem, we are assuming that situation. So, just go through here. So, from here, starting on from here, the water is collected in this channel, and it is flowing like this. So, at a rate of q star, it is being collected, the entire thing. So, we can suggest now for the rectangular channel V is equal to T for rectangular channel, A is equal to B y, right. What is, let me ask you a simple question now. Okay, I will just redraw the thing here. So, this is the horizontal channel, we are looking the longitudinal profile. So, the flow in the channel, it is having a free outfall. Okay. So, I will just redraw the thing again like this. So, in this case, what will be the depth of flow at the free fall outlet? This should be equal to the critical depth. It should be equal to the critical depth in the flow. So, if that is clear to you, then discharge at free fall outlet. What is the discharge at free fall outlet? If you recall the thing, we had suggested that water is slowly increasing. Water is slowly increasing from this section to this section as it goes downstream. So, the rate of increase is q star per unit length. So, we give the quantity q 0, this is nothing but q star into the length of channel. So, this q 0 is the discharge at outlet, or you can suggest now that q star is nothing but equal to q 0 by L. Also, for any small elemental length in the channel, say dx, you can easily identify the change in discharge dq. This is nothing but equal to q star into dx. So, this quantity now it can be easily suggested, you can integrate this thing dq is equal to into q star dx, or you will find that discharge at any section along the channel, q, this will be nothing but equal to q star into x, because q star is independent of length x. So, therefore, you can take it out and integral dx will give you x. So, we will use the same relationship. So, we know that average velocity at any section, this is nothing but discharge divided by the area of flow, or q is equal to v bar a. These things you have been dealing it earlier onwards. Now, q is equal to q star into x. Therefore, your average velocity becomes q star into x divided by area. For this rectangular channel, v bar is nothing but q star x by b y. So, what do you get from this thing? Substitute these quantities in dynamic equation. So, dy by dx is equal to minus twice capital Q is q star x. So, this becomes q star square x by b y, I beg pardon, this becomes q star squared x by g b squared y squared, the whole thing divided by 1 minus q star squared into x squared b by g b cube y cube. So, we have just substituted all the quantities. You know what is q. So, q is equal to q star x, that is substituted here. Instead of the top width t, we have substituted the width b, and we got this